You are asleep in your room, but a fire has broken out in the hall, and smoke is pouring in through the partially open door. You need to close the door as soon as possible, and you're going to try to push it forward. So there's the door, and you need to impart the maximum impulse here. You have a ball of clay and a bouncy ball, each of the same mass. If you throw the clay at the door, it will stick to it. If you throw the bouncy ball, it will bounce off. You only have time to throw one thing at the door. Which should you throw, the clay or the bouncy ball? So the idea here is that the change in momentum is equal to F net delta T, the impulse. And so for the clay ball, delta P is the final minus the initial is equal to 0 minus mv initial. And assuming you have the same throwing speed for both of them, for the bouncy ball, it ends with negative mv initial, and minus mv initial was the positive, is negative 2 mv initial. So the bouncy ball changes momentum by twice as much, so imparts twice the impulse to the door. So it's B. Okay, it says that questions 11 and 12 both refer to the following situation and diagram. A 3 kilogram chunk of ice is sliding at 6 meters per second on the floor of an ice-covered valley when it collides with a 5 kilogram chunk of ice that is initially at rest. The surface is frictionless everywhere. Question 11. Assume the collision of the two chunks of ice is perfectly inelastic, meaning that they stick together. After the collision, how high above the valley floor will the combined chunks go? So we have the collision, which conserves momentum. So you would say that P is equal to P prime. So P initial is M1 V1 plus M2 V2. And P final is they're stuck together, so it's M1 M plus M2 times V final. And so, or the prime, right after the collision. And also this one, V2 is equal to 0. So you just say that V prime is equal to M1 V1 divided by M1 plus M2. 3 times 6 divided by 3 plus 5, 2.25 meters per second just after the collision. And then it will go up until this V final is equal to 0. So what will happen is that conservation of energy while sliding. So E initial equals E final. KE initial plus PE initial equals KE final plus PE final. So the KE initial is 1/2 M1 plus M2 V prime squared plus 0 is equal to the KE final. It's going to stop at the end, plus M1 plus M2 times G times H final. And we're trying to solve for H final. We can divide both sides by the total mass. Turns out it doesn't matter. Solve for H final is equal to V prime squared divided by 2 times G. So it's 2.25 squared divided by 2 times 9.8. Squared divided by 2 equals divided by 9.8 equals 0.258 meters up the hill. That's B. Question 12 refers to the same situation, but it says assume the collision of the two chunks of ice is head-on and elastic. This means that during the collision, all motion is along a line, momentum is conserved, and also kinetic energy is conserved. After the collision, how high above the valley floor will the 5 kilogram block go? So in this case, what you've got is M1 traveling at some speed, V1, and M2, which is at rest. And then after, M1 is traveling at V1 prime, and M2 is traveling at V2 prime. And for elastic collisions, we have the handy equations from my aid sheet, which we did in class 22, which is that V1 prime is M1 minus M2 over M1 plus M2 times V1. And V2 prime, which is what we care about, is 2 M1 divided by M1 plus M2 times V1. So that's what we want, because we're looking for how high does M2 get up? And so V2 prime is equal to 2 times 3 times 6 divided by 3 plus 5. It's just twice the last one, so this is now 4.5 meters per second. And again, after the collision, you use conservation of energy while sliding. E initial equals E final. So 1/2 mv m2 times v2 prime squared plus 0 is equal to, it stops, times m2 times g times h final. In this case, it's the m2's that cancel. H final equals v2 prime squared divided by 2 times g, 4.5 squared divided by 2 times 9.8 squared divided by 2 equals divided by 9.8 equals 1.03 meters, which is E. A man sits in a canoe floating in a lake. The only thing in the canoe other than a man is a large rock. So there's a guy and there's a rock. If the man throws the rock away from the shore with a speed of 8 meters per second, what will be the resulting speed of the man and the canoe? Assume the man has a mass of 75 kilograms, the canoe has a mass of 35 kilograms, and the rock has a mass of 15 kilograms. So I would just say initial, P equals 0, everything at rest. And then finally, what will happen here is that this rock, mr, will be going in one direction at VR is equal to 8.0 meters per second. And then what will happen is that the total, this is P initial is 0, P final is equal to 0, is going to be mr VR minus the mass of the canoe plus the mass of the man, all times this final velocity of the mass and of the man and the mass. So I'll just solve for V. So you get V is equal to the mass of the rock divided by the mass of the canoe plus the mass of the man times the velocity of the rock. So we're going to have 15 kilograms divided by 75 plus 35 all times 8. 15 divided by, open parentheses, 75 plus 35, close parentheses, equals, and then times that by 8, and you get 1.09 meters per second. That's closest to 1.1 meters per second. Okay, question 5. A truck of mass mt is moving with an initial speed v. So let's write this down. And collides with a stationary car of mass mc. The truck and car remain locked together and skid a distance d before stopping. Okay, there's a bunch of parts of this problem. I guess what happens is that then they crash, and you've got mt and mc in a totally inelastic collision, so they're stuck together. So I'm going to call that V2 or something like that. And then what will happen is this screech along some distance d, so that you'll end up with V3 is equal to 0. It stops at some distance. Distance d before stopping. The coefficient of kinetic friction between the wheels of the vehicles and the road is mu sub k, so it's this sliding friction. Which of the equations below gives the truck's initial speed? So we're trying to find v, is question mark. So what we're going to do is conserve momentum during this collision from the initial instant to v2. So P, I'll call it P0 equals P2 or something like that. So that's going to be the mt times v, that's the only initial momentum because the truck's the only thing moving, is equal to mt plus mc all times this v2. V2 is what we don't know, unfortunately. But I can already tell you that v here is going to be mt plus mc all divided by the mass of the truck times something. We don't know what that v2 is. So, but if I look at all these answers, I'm starting to see that I like E, and I don't like some of these other ones as much. I also like A. It's probably A or E. So that's kind of good. So if I'm out of time, I've already whittled this down to 2. So what's V2? So what's going to happen here is I've got V2 is the initial. So we're going to use, first of all, a force diagram. You've got normal force acting up. You've got M total or something like that acting down times G. And you've got this Fk acting backwards, which is mu sub k times N. You've got the sum of all the forces in the y direction is equal to 0. That's N minus M total times G. So that means that N equals the mass total times G. And you can plug that into this friction equation so that the sum of all the forces in the x direction is equal to negative F times K. And that's just equal to negative mu sub K times M total times G. And so A sub x is equal to the sum of all the forces in the x direction divided by the mass total. That's the whole thing is sliding along here, and that's just going to be equal to negative mu sub k times just times G. So now I'm going to go way back to chapter 2 for this kinematics equation 2.7, which is that 2 times A sub x times this D is equal to V, it's going to be V3 squared minus V2 squared. And we're trying to solve for V2. This is 0. So I would say that V2 squared, negative, is equal to 2 times AX times D. And so that's going to be equal to 2 times negative mu sub K times G times D. So the negatives cancel there, luckily, because V2 squared should be a positive number, is equal to just 2 times mu sub K times G times D. So V2 is equal to the square root of 2 mu sub K times G times D. And now we can take this, since we know it, and plug it in to this over here, and we got that speed is equal to, I'll put this in parentheses, mt plus mc, all divided by mt, and multiplied times the square root of 2 times mu sub k times G times D. So now this is starting to look a lot like question A. In practicals, you send a cart of mass 0.55 kilograms along a track with an initial velocity of 72 centimeters per second. It rolls for a while, I guess it's slowing down, then collides with a fixed force sensor at the end of the track and reverses its direction. Shown as the motion sensor data giving velocity versus time. The sensor was set to record 60 samples per second. Which of the following is the best estimate for the change in momentum? So find delta P in the cart during the brief collision at t equals 1.3 seconds. So it's talking about this particular collision and trying to find delta P. And remember, P is a vector. So it starts off positive, goes to negative. Let's try to estimate here. That's, I guess, V initial is going to be plus 60 centimeters per second, which is equal to plus 0.60 meters per second. And then end just after the collision, it seems like V final is equal to maybe negative 55 centimeters per second. Just to sketch this out a little, you've got a cart which is 0.55 kilograms, and it's going to the right, and V initial is equal to 0.6 meters per second. So the P initial there is going to be plus 0.55 times 0.6, 0.55 times 0.6. It's going to be plus 0.33 kilograms meters per second. And then that's your initial situation. Your final situation is just the cart is now reversed its direction because it bumped off the bumper or something like that. It's still 0.55 kilograms, but V final is now this negative 0.55 meters per second. So P
final is a negative number. 0.55 times, actually 0.55 would be numerically the same, so it's 0.55 times 0.55, and you get P final is negative 0.3025 kilograms meters per second. So what that means is delta P is P final minus P initial, which is negative 0.3025 minus 0.33, negative 0.6325 kilograms meters per second is the change in momentum that we're trying to find. Let's see if that matches up any of these. Yeah, so the closest answer, version A here, is D. Two forces impart impulses to a hockey puck which can move with no friction on an icy surface. Shown is the trajectory of the puck's motion in the XY plane, which is the result of these forces. The numbers correspond to successive clock readings that are marked on these force graphs. Okay. Which pair of graphs shows the time dependence of the x and y components of the sum of forces exerted on the puck, which could result in this trajectory? There's a hit here at 1 and a hit here at 2. So at 1, what happens is the trajectory, I think it must have initially been going like V0, going up, and then this is V1, still going up, but now it's going to the right. So what's happened here is that there's been delta P x is positive. So that must have required plus F x force, an impulse, over a small amount of time. And then what happens is that V2 is now going purely horizontally, so it's lost. It's still got this horizontal motion, but it's lost its vertical motion. So I would say that delta Py is, this is at 1 and this is at 2, is negative. So what it means here is that at t equals 2 seconds, there's an Fy, like a negative Fy impulse force. So what we're looking for is at 1 second, a plus force, and then at 2 seconds, a negative y force. And nothing from the y at 1 and nothing from x at 2. Actually, look at that. The answer is A. Just check the other ones. This has got 2 positives. That's not right, because this would speed it up even more in the y direction. This has a x force at 2 seconds, which that's not right. Nothing at 1, so that's wrong. This is wrong. All these have something happening at 2, which is wrong, and 1. So I think the only one that makes any sense is A. It says, a 920 kilogram sports car collides into the rear end of a truck stopped at a red light. So the vehicle is locked together, so this is an inelastic collision. The brakes are locked, meaning that the two vehicles skid forward, so it's sliding friction 2.8 meters before stopping. This is a 1D problem. The police officer estimating the coefficient of friction between tires and road to be 0.8. Calculates the speed of the sports car at impact. What was that speed? Okay, great. And basically, there are 2 things that are happening here. One is the collision, which is going to conserve momentum, and then the next is the skidding, which is going to conserve energy. And so I'm going to break this up into 3 separate times, so that at the beginning you have the mass of the car, which is 920 kilograms, and it's going at some speed you don't know, V1 of the car. That's what you're trying to find, so need this. And then the mass of the truck, which is 2,300 kilograms. This V1 truck is equal to 0. And then they collide, and so what happens is that now they're stuck together. I can sort of say mass total is equal to 920 plus 2,300. 920 plus 2,300 is 3220 kg. That's going at some V2. And then 3, what'll happen is that whole thing will slide some distance d, so that V3 equals 0, and this is m total. And what will happen is that there will be some kinetic friction, which will conserve energy here. So from 1 to 2, what we're going to do is conserve momentum. P initial plus J is equal to P final. And from 2 to 3, what we're going to do is conserve energy. So that energy initial plus the work is energy final plus delta U internal. So we can just say that from 1 to 2, it looks something like this. You've got the initial, P initial of the car, and then the P initial of the truck, which is 0, and then the impulse, which is 0, is equal to the P final of the total. And then from 2 to 3, what happens is that you've got your, that thing is sliding, so the kinetic energy initial plus the work is equal to the kinetic energy final plus the delta U internal, which is equal to the Fk times d. That's where all the energy goes. This equation, which is that the mass of the car times the V1 of the car plus 0 is equal to the mass total times V2. And then from this diagram, you've got 1/2 m total times V2 squared, that's initial kinetic, is equal to Fk times d. And the thing about the Fk is that Fk is equal to the normal force times mu sub k. And if you have the normal force acting up and m total g acting down, and this is the y direction, and a sub y equals 0, so the sum of all the forces in the y direction equals 0, then what that means is that normal force equals m total times g. So what you end up with is that m 1/2 m total times v2 squared is equal to mu sub k times m total times g times d. And you can cross out the m total on both sides of that energy equation to solve out for V2. V2 is going to end up being the square root of 2 times mu sub k times g times d. And we're going to sub that back into here, which is to say that V1 of the car is equal to m total divided by the mass of the car times this V2, square root of 2 times mu sub k times g times d. And I think we have all these numbers. 3220 kilograms for both the objects, 920 for the car, times the square root of 2 times 0.8 times 9.8 times 2.8, 3220 divided by 920 times the square root of 2 times 0.8 times 9.8 times 2.8. I get V1 of the car is equal to 23.19, so, and that's meters per second. V1 of the car, so the initial speed of the sports car was 23 meters per second. And I think if you times by 3.6, you get, that's around 80 kilometers per hour. Not an unreasonable speed. Bit fast, be crashing, but that's why they slide so far. And that is it.